Anyways, so right. So what we are solving is this IIT Jam 2021, and this is question number 11. Yeah. So you have the question. So MNR be the real vector space of n by n matrices with real entries. Okay. And A is a particular matrix, and consider the subspace W of MNR spanned by powers of a single matrix. Then what is the dimension of W over R? Right. So you have MNR. So MNR you understand, right? This is as a vector space, it is just Rn square, right? And but yeah, so this is okay. But you are looking at this this thing. Is it the space generated by these matrices? So these are the vectors now. Okay. Identity matrix and this matrix. Okay. So what will be the dimension of this space? That is the question. What is the dimension of W? So the options are, usually I won't write the option, but let's just write it. Infinity n square n at most n. So tell me
I,
whatever you can about this.
I think it would be n.
Okay. Now you first try to check yourself. Check by yourself if you think few minutes and then you tell me. Think and say. Don't just say like. So we have not studied the theory to answer this question. Okay. But you could still do this by option elimination. And that's not cheating. I mean, you can still actually do it. But don't say anything. Think and take examples and see and then. But as I repeat, we have not done the theory to answer this question.
Okay.
Okay, but you can still try with examples.
अच्छा यहाँ पे स्पैन बाय डॉट 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 दिया हुआ है तो मतलब
And by
स्पैन बाय आई एन ए स्क्वायर these are the also matrix from M and R
right
and अगर if we take the elements of one matrix
uh,
then they they should be also spanned by the elements of these matrices.
elements of matrix. What does that mean? Elements
If
of
I
a
take
matrix.
matrix A B C D,
Uh,
then A B C D they should be also spanned by the elements of I N A square, all that.
I don't understand because these are numbers and these are matrices. So how do matrices span numbers? You're trying to say something, but I'm not understanding. Yeah, you can think of this as a tuple and then you can say, right? Means I want you to say it properly because that's a better thing. If I try, I can understand what you're saying if I ask you, but you should do it without me asking you anything. What is it that you want to say? Ask yourself and then say it clearly. No?
Uh, um, एक मैट्रिक्स ले लेते हैं फ्रॉम एम एन आर कोई भी
Uh,
एनी arbitrary
okay. Okay.
suppose that is a to the power b.
A to the power B.
Yeah,
Okay.
I mean n is given, so you take any other variable. We can take also a to the power n, no problem.
Okay. Okay.
And we can write it as c naught in plus c1 a plus c2 a2 a square and dot dot dot. एंड जबकि हम लोगों को इसको मतलब स्पैन बाय सम मतलब डायमेंशन दिखाना होगा तो वी कैन टेक ए आर्बिटरी नंबर आई मीन सपोज मान लेते हैं सी एन ए टू दावर सी एम सॉरी सी एम ए टू दावर एम.
Okay.
अब हमें दिखाना पड़ेगा अगर ये लिनियरली इंडिपेंडेंट है तो n शुड बी एट मोस्ट m समथिंग लाइक दैट.
ये linearly independent. What is linearly independent? Which set is linearly independent?
We don't know how much this I and a squared goes to.
It may go forever, right? And there is no guarantee. May never become zero or something. It may go forever, but at one point they may start becoming dependent. Yeah. So you are maybe, yeah, you are trying to say something, but I understand now. I understand, but that will get a bit complicated. Yeah.
Okay.
Let us. That question will be answered soon, but Let us see. So why do you think infinity is not possible? Right? Because W is a subspace, right? So dimension of a subspace of a vector space is always less than or equal to that of a vector space, right? And this dimension is n square. So this dimension will be at most n square.
Yeah.
Okay? And that is not has nothing to do with this subspace, any subspace for any vector space. So this is automatically not possible. It's they're doing a reasoning which will work in general. So general reasoning. Okay. Let's look at some reasoning for second one. Why will it? Can you explain why is it not n square? Do you have an explanation why is it not n square?
Um, because W is the subspace of MNR and it has and it is given that spanned by A square. So all elements couldn't be in the set W.
So you are saying that it's a proper subspace. Just say that, right? It's a proper subspace. So why is it a proper subspace always? Give a reason. Give a reason. Think and then.
It's written that it's spanned by I and A square.
Right,
So
but it may end up, but it is not written that it cannot be all of M and R. That's not written. That you are saying, which is true, but you have to prove it. And it is not
A is
completely
an
out.
argument of MNR.
So then give an example.
Okay.
See, if you say that this is not n square, this means that it is not n square for some a, right? माने किसी एक a के लिए ये fail हो रहा है इसलिए ये false है ना? So you just give an example then. Just give me a matrix. Just take the zero matrix, right? Okay, fine. Take the zero matrix, then the dimension is 1. So this also rules out this. Because nowhere it is written that A cannot be 0. I can take A to be 0 matrix. Then the dimension is 1. But
It is given that the real entries are n greater than equal to.
n is given to be greater than equal to. That we are not concerned with, right? Right? That is fine. That is nothing to do. Right, maybe. But you should do this homework for any A. W is a proper subset. Okay, this is your homework. Think about it. कि ये नहीं है कि सिर्फ ए जीरो लेने से वो सबस्पेस हो रहा नहीं तुम कुछ भी ले लो वो एक सबस्पेस होगा प्रॉपर सबस्पेस होगा किसी भी एक को यू कैन ऑलरेडी फील राइट यू कैन ऑलरेडी फील अ लिटिल बिट बट it's true. You see the difference between these two things, right? First is saying that this dimension is not n square. It's for false. This is false because it's not always true. But now we are saying given a, given a, given any a, this dimension is not equal to n square. Okay. So this is false for every a, I'm saying. That you should think. Okay. So that is your homework number 1. And homework number 2 is that find a such that dimension W is equal to n. Is equal to n. माने n हो सकता है.
Find a such that
The dimension of W is equal to n. Okay. And this is a very simple question. Actually. You have to just take some simple A like diagonal matrix or something, and you will understand. Okay.
okay.
Diagonal matrix it just becomes like Rn, so its dimension is n, but you should check.
N.
So you can feel that. So our question is done, right? It's at most 10,
Just by elimination. Wow.
right? But we are not cheating anywhere. We are not cheating. It's correct, right? Our proof is not a. Its proof is correct. Okay.
Okay.
But yeah, if you want to directly show that it is at most 10, yeah. So suppose that's the point. Suppose if there was an option, uh, yeah. So the problem is that because of the zero matrix, all the options go away, right? Any kind of option will not be able to. Doesn't seem like it can fool you, right? But what if it is at most n minus 1, and this is not there, and there is n, right? So you have to show, I mean, in this case, I mean, yeah, maybe at most n is also there. Yeah, this logically, this also cannot fool you because then both of them are correct. Both can also be correct. But this will not be correct if it's multiple choice. This will not be correct because of this. Find a such that it is equal to n. That's why you should do this one. But all this is fine. Let us actually come to a mathematics. And that mathematics is Cayley-Hamilton theorem. That is the theorem which solves this problem nicely.
Theorem name Hamilton theorem.
Cayley-Hamilton,
Acha.
you have heard of it, right?
Yes.
It's a very important theorem. Cayley-Hamilton theorem. And if you want to really do it properly, it's called Nakayama level in commutative algebra. Yeah. So what does the Cayley-Hamilton theorem say? So the point is that the Cayley-Hamilton theorem is usually stated in some way, but you have to interpret it about its fact about dimension. It doesn't directly say like, but that's a useless statement, I say. Cayley-Hamilton theorem says that given any matrix A, determinant of A minus lambda I is equal to 0. I mean, no, what am I saying? Sorry. So you look at this polynomial and you call this polynomial P lambda. Okay, call this polynomial P lambda. The Cayley-Hamilton theorem is saying that P of A, so this is P lambda, and the claim is that P of A. Now be careful. Okay, if you look at this expression, A is fixed. Okay, fixed, but nothing is assumed about A, so it's arbitrary. Look at determinant of A minus lambda I. What kind of thing is that? After you expand and use some basic definition of determinant, any definition that you know, you see that it's a polynomial in lambda, some complicated polynomial that we don't need to know, but you know it's some polynomial in lambda.
Yes.
Fine? Right. So this basically is a polynomial in Rx or R lambda. It's an element in R lambda in this ring. Okay. But then when I say PA is 0, this is saying that in that polynomial, wherever lambda is appearing, you put A every. Okay? I mean, it is self-understood, but I'm still explaining. Okay? So you just put you put A in place of lambda. That is all. So what does Cayley-Hamilton theorem claim? Cayley-Hamilton theorem is claiming that this is equal to 0. It is not so easy to prove maybe that this is equal to 0. But
Yeah. But how we are using this in this question?
that you will understand yourself. First, let's understand more serious stuff. That will become obvious. First, let's think about why this is true. That you will figure out. Just ask yourself what is the degree of this polynomial. So you understand the statement, right? This is the Cayley-Hamilton theorem. And right. Let me also say one thing. This is going to be a very important polynomial. This is characteristic. This is called the characteristic polynomial of the matrix. Okay. This is the characteristic polynomial of the matrix. Very important polynomial that we associate to matrices. To every matrix, we associate a polynomial called the characteristic polynomial. All your eigenvalues, things will come using this. So, do you see why? Do you see a proof of this? One false proof that goes around. Just to remember it, you just put lambda equal to a, right? So this is obviously 0.
Yes.
But this is wrong. This is the wrong proof. Can you think why this is wrong?
Um,
It's difficult difficult to think why this is wrong because it gives the correct result. So when we get the correct result, then it's difficult to know why the explanation is wrong. That's a more subtle thing, right? That's more subtle. You see, this PA is not a number. This PA is not a number. So that's the first thing, right? I mean, it's wrong because this PA is not a number. So this is a matrix, the n by n matrix, which is 0. That's quite clear. It's not a number. And this thing is a number which is 0. So how does it prove anything? It doesn't prove anything. That's
then determinant of a minus lambda is also a number, no?
yes, it's a number because you're taking determinant. So you prove that some number is 0, fine. But how does it
Then
prove
why
that this?
p of lambda?
Sorry.
We're writing as p of lambda.
Uh,
Lambda is any
yeah, arbitrary. Exactly. But for any arbitrary, but when you put a value there, you get a number, right? So
yes.
yeah. So if you put anything, you get a number. Even if you put a matrix in place of lambda, you get a number. And then you have just shown that this number is 0, right? And that is not the same as this P of A. Because this P of A is a matrix,
Yes.
right? I mean, there are many things which are wrong here. You can sense this proof is wrong. It still gives the correct fact, but the path is wrong. It's wrong. And it will soon start giving wrong results when you generalize. I think, I mean, I don't know. But the fact that it still works is quite amazing that you get a 0 matrix. There should be another Yeah, like that determinant just gives you a number, and yeah, one can explain this by saying that something is not a ring homomorphism, but yeah, but this is quite clear that if you put p of, but the point is that if you put p, if I put lambda equal to a, okay, then I'm looking at a, I'm just trying to understand this for myself. Uh, if I put lambda equal to a, then I get a homomorphism. Yeah, you cannot put lambda equal to a. Anyways, yeah. So let's come forward and try to maybe understand why this is true. So actually, I don't quite recall a proof right now. I mean, I can give you proofs using other ways, but
Okay, let me read it at first, then I will ask you.
all right. Yeah, you can read it. So, but it will be slightly complicated. But anyway, so okay, not Nakayama algebra, right? It's called Nakayama lemma. I'm sorry. Today I was reading about Nakayama algebra. That's a different thing. Something self-injective algebra. Some example of that is the Nakayama algebra. This is not. This is Nakayama lemma. It's easy. Yeah. So that is one way, but we avoid that. Yeah. So one way is like this. Okay. That yeah. Okay. Anyways, so you try to read it. I think it's a bit difficult to explain at the moment. Yeah. Without the concept of eigenvalues, so if you know the concept of eigenvalues or just one. Okay, anyways, let me explain this. I think it's a bit rushed here. Yeah, so okay, if you assume this, then the problem is done, right? Because you know that the degree of this PA, or I mean degree of P, yeah, degree of P is at most is less than n, right? Less than equal to n, right? That's clear because it's the
Yes.
determinant of a n by n polynomial, n by n matrix. Yeah, just look at this matrix, and when you expand this, you will see that lambda will come power n times at most, right?
Yes.
You can sense that, but you should again prove it yourself. Something like this, right? Other things, many other things. But when the way you calculate determinant, you can understand a degree will be actually equal to n always. Correct? The way you calculate determinant, you can sense that. Yeah, I don't want to explain it, understand it. So that's the thing. I mean, the degree is equal to n. What does this mean? This means that this P of A will look like what? P of A will be what? Some A to the n plus something. I mean, that something is a useful thing, but we'll talk about it later. And something like this, and so on. This is equal to 0, right? That is what this
Yes.
thing says, right?
Hmm.
P is the point. And this means that these vectors are dependent, right? This implies that a to the n, a to the n minus 1, a to the n minus 2, these are dependent. No?
Why dependent?
You see, you have a linear combination, right?
Yes.
So that's why they are
But we don't know that C1, C2, all those will be zero.
so this is non-zero, right? One is not equal to zero.
Ah, yes.
Right. That's it. So the dimension is so the dimension is actually uh, yeah is at most n, right? Because there are n plus one vectors. So you have said that oh, did I say anything wrong? Okay, so you have found so these are n plus one vectors and they are dependent. So you have found a you have found a collection of n plus one vectors which are dependent. So does it prove that the dimension is that? So you should ask, why can't you have some other n plus one independent?
Yes, why?
Right? So basically, you see the subspace that you had W, right? Yeah. And if you look at the generating set, you look at the generating set. This was a generating set by definition, right? Infinite generating set, but this was a generating set by definition. Okay. And in this generating set, we have already explained that this is a dependence. Okay. We have explained that a to the power n can basically be generated using these things. Correct or not?
Yes.
Right? And similarly, you can prove that a to the n plus 1 can be generated by the first n things. Just multiply by a in the equation.
Yeah.
And so on and so on. So it's important actually to explain this maybe. So basically, and then you can further cut off, right? This n plus, yeah. N you will get this again, you can write in the lower using the lower things. This is comes in something called integral dependence. We'll talk about later. It's important because we are in a field, otherwise it's not true. So that's it. So basically, you have another generating set which is size n. So you have a generating set of size n plus 1, n. You have a generating set of size n, so the dimension can be at most n. Correct? You have a generating set for the generating set. So that will also be a generating set. Generate the generating set will generate everything. The dimension. So Cayley-Hamilton theorem is basically saying that, nothing else. Yeah. And it is actually saying mostly just that. But it's not such an obvious fact, right? To begin with, if n square dimension space, why will a cyclic kind of thing happen? Okay. So yeah,
And the given problem where you gave me that find a such that dimension of W is equal to n, the
hmm.
W is spanned by this set only that is given.
No, but there is a problem, right? You have to but why is the dimension of that n? That could further have some dependent vectors. We did not say anything about that, right? A to the n minus 1 could also depend on the other ones. Right? There could be some other Cayley-Hamilton theorem, right? Stronger Cayley-Hamilton theorem. You have to prove that there is none. You have to give an example. Right? That's the problem. Because already you saw, right? Zero may. Yes. Think about it. Yeah. So what to do? Maybe. Yeah. I wanted to. I want to just give a proof of this. Okay. So let's meet after 5 minutes if you want, right? And then we can just explain this a little bit, and then we can stop.
Okay. But can you just tell me what is the next question we are gonna solve?
question, no, I'll just try to show you why this is true. Kelly Hamilton theorem. That is important to understand. Some analysis, some real analysis we can use also and prove it.